Hello students, today's topic is electrochemistry. It's a branch of chemistry which deals with study of electrolytes and behavior of electrolytes. It's about the term conductors, the compound or substance which allows the flow of electricity. They are called as conductors. And there are two types of conductors: metallic conductors, and electrolytic conductors. See, in metallic conductor, the flow of electricity undergoes without the decomposition of substance. And here, electricity flows due to the flow of electrons. That kind of conductors are called as metallic conductors. Next one is electrolytic conductors. Electrolytic conductors. In electrolytic conductors, flow of electricity undergoes decomposition of substance, and electricity flows due to the movement of ions. That kind of conductors are called as electrolytic conductors. Now, next about the term conductance. Conductance. Now, when potential difference is applied between two electrodes, the movement of ions takes place towards the oppositively charged electrodes. Negative ion move towards the anode, and positive ion it move towards the cathode. So due to the movement of ions, electricity flows, and the ease of flow of electricity is called as conductance. Ease of flow of electricity is called as conductance. Or conductance is the reciprocal of resistance. Reciprocal of resistance. Therefore, unit of conductance per ohm or Siemens. So this is about conductance. Now, about the specific resistance. Specific resistance. Now, resistance is directly proportional to length of the electrode. R, resistance, directly proportional to length of the electrode, and inversely proportional to area of cross section. Therefore, R is proportional to L by A. R is proportional to L by A. By taking proportionality constant, R is equal to rho into L by A, where rho is resistivity. Therefore, the resistivity rho it is equals to R into A by L. R into A by L. Now, so about the unit of resistivity. Unit ohm meter or ohm centimeter. Okay, this is about unit of specific resistance. Now, next about different types of conductance. That first one is about specific conductance. Is represented by kappa. Now, specific conductance is defined as the conductance offered by the solution which contains length of the electrode is 1 meter and area of cross section is 1 meter square. Such type of conductance is called as specific conductance. Now, K is equals to reciprocal of resistivity, or this also is equals to 1 by R into L by A, Here L by A is called as cell constant. L by A is called as cell constant. Now, say about the unit of specific conductance unit per ohm. Okay, per ohm, per meter, or Simon per meter. This is about specific conductance. Now, next about equivalent conductance. Equivalent conductance. Equivalent conductance is defined as the conductance offered by all the ions present in a solution containing 1 gram equivalent of electrolyte. 1 gram equivalent weight of an electrolyte. That kind of conductance is called as equivalent conductance. Equivalent conductance is represented by lambda EQ. Now, it's about the SI unit of equivalent conductance, Simon meter square per equivalent. Okay. So, equivalent conductance is also written like this: lambda is equals to K into V, or K into 1000 divided by equivalent weight, or we can write like this: K into 1000 divided by normality. 1000 divided by normality. It is about equivalent conductance. Next, about molar conductance. So, molar conductance is the conductance offered by all the ions present in a solution containing 1 mole of an electrolyte. So, it is called as molar conductance. SI unit of molar conductance. SI unit of molar conductance. Simon meter square per mole. Simon meter square per mole. Now, so molar conductance, lambda m, it is equals to K into V. K is equals to 1000 divided by molarity. 1000 divided by molarity. Okay. So, this is about the term molar conductance. Now, next about the relationship between equivalent conductance and molar conductance. Relationship between molar conductance and equivalent conductance. So, molar conductance lambda m, it is equals to equivalent conductance into n, where n is a factor, equivalent factor of the electrolyte, which indicates charge on the anion or charge on the cation or basicity of acid or acidity of a base, or n can be calculated using molecular mass divided by equivalent mass. Molecular mass divided by equivalent mass. So, this is the relationship between molar conductivity and equivalent conductivity. Now, the factors affecting conductance. So, what are different factors affecting the conductance? There are several factors affecting the conductance. First, about extent of ionization. The conductance is directly proportional to extent of ionization. Extent of ionization. So, greater the ionization, greater is the conductance. Next, about temperature, directly proportional to temperature. Conductance is directly proportional to temperature. Now, next, about mobility of ions and also size of the ions. Now, conductance is directly proportional to mobility, ionic mobility. and inversely proportional to size of the ion. Inversely proportional to size of the ion. Size of the ion or ionic size. Okay. And one more factor about viscosity of the solution. Conductance is inversely proportional to viscosity of the solution. Viscosity of the solution. And also it depends on the nature of the electrolytes. So these are the factors affecting conductance. Next, about nature of electrolytes. So there are two types of electrolytes, weak electrolytes and strong electrolytes. The electrolytes, when dissolved in water, they dissociate partially. Such electrolytes are called as weak electrolytes. Weak electrolytes. So weak acids and weak bases are example for weak electrolytes. Strong electrolytes are those electrolytes which undergo almost complete ionization when dissolved in water. Strong acids like HCl, sulfuric acid, nitric acid, as well as strong bases like sodium hydroxide, barium hydroxide, salts, sodium acetate, potassium nitrate, potassium chloride. All these are examples for strong electrolytes. So these are the two different types of electrolytes. Now, its effect of concentration on specific conductance, equivalent conductance and the molar conductance. The concentration. Its effect of concentration with respect to specific conductance, equivalent conductance and molar conductance. Now, first about specific conductance. Specific conductance. Now, specific conductance increases with increase in concentration. Increases with increase in concentration. Increase in concentration. Why it increases? When concentration increases, number of ions per unit volume increases. Therefore, specific conductance increases. Now, equivalent conductance and the molar conductance. Equivalent conductance and molar conductance. Molar conductance increases with decrease in concentration. Increases with decrease in concentration. Concentration of the solution. So this is about molar conductance and the equivalent conductance. So why molar conductance and equivalent conductance increases with decrease in concentration? Decrease in concentration with dilution, that increases the ionization. As a result, equivalent conductance and molar conductance increases. So this is about effect of concentration on different types of conductance. Okay. Next, about Debye-Huckel-Onsager equation. So in order to calculate molar conductivity of a solution, this equation is used. Molar conductivity as well as equivalent conductivity. Okay. Now, Debye-Huckel-Onsager equation. Now, so in order to calculate molar conductivity of the solution, this equation is used. Now, so according to Debye-Huckel-Onsager equation, molar conductivity with respect to concentration is equals to molar conductivity at infinite dilution minus A into root C, where this indicates the molar conductance with respect to concentration. This is at infinite dilution. A is a constant and C is concentration of the electrolyte. Now, when you plot the graph, molar conductance with respect to concentration versus the concentration of the electrolyte. For a strong electrolyte, it gives a straight line. This is for NaCl, sodium chloride. By extraplotting the graph, this indicates at zero concentration, this indicates molar conductivity at infinite dilution, and slope of the graph that gives the value of A. So this is applicable for strong electrolyte. When you consider weak electrolyte, it gives a plot like this. Okay. So when the concentration decreases, this value increases. Therefore, it is not possible to calculate molar conductance of weak electrolyte at infinite dilution. So in order to overcome the demerits of Debye-Huckel-Onsager equation, one more law is given. That law is given as Kohlrash Law. So what is Kohlrash Law? At infinite dilution, molar conductivity of weak electrolyte can be calculated by knowing the contribution of molar conductivity of individual ions present in it. Okay. Therefore, it can be represented like this. Molar conductivity at infinite dilution, zero concentration, infinite dilution, that's equals to cation and anion. Now, if you consider the electrolyte like this, AX, BY, that dissociate to give X, A plus Y, Y into B, X minus. So when you consider the molar conductivity at infinite dilution with respect to these two ions, X into molar conductivity of A cation plus Y into molar conductivity of anion. Here which is anion? B is anion. Okay. So about the application of Kohlrash Law. First one, degree of ionization we can calculate by alpha is equals to molar conductivity with respect to concentration and molar conductivity at infinite dilution. That gives value of alpha. Similarly, using this we can calculate molar conductivity of weak electrolyte. See, in order to calculate molar conductivity of weak electrolyte, we have to take 3 strong electrolyte. Now, for example, molar conductivity of acetic acid at infinite dilution can be calculated using sodium acetate, sodium chloride and hydrochloric acid. Now, look here. Acetic acid is a weak electrolyte. So molar conductive weak electrolyte can be calculated using 3 strong electrolytes like sodium acetate, CH3COONA, sodium acetate. Okay. Then hydrochloric acid, hydrochloric acid minus molar conductivity of sodium chloride, NaCl. Now, here molar conductivity Na plus ion Cl minus ion gets cancelled. The remaining is acetate ion and H plus ion. So by knowing this, we can calculate the molar conductivity of acetic acid at infinite dilution. Okay. So this is about Kohlrash law. Now, next about the Faraday's law of electrolysis. Okay. What is electrolysis? Decomposition of an electrolyte by passing electricity through it. That process is called as electrolysis. So Faraday's first law of electrolysis. Faraday's first law of electrolysis. Now, so during electrolysis, mass of the compound deposited at any electrode is directly proportional to quantity of current passing through it. Let mass of the compound deposited be W. Quantity of current passing through it, Q. So W is proportional to Q, where the Q is the product of strength of current in terms of ampere and time in terms of second. So Q is equals to IT. So W is proportional to IT, or W is equal to ZIT. Here Z is called as electrochemical equivalent. And Z can be calculated. Z is equals to W divided by IT. This is about Faraday's first law of electrolysis. Now, when a metal ion undergo reduction, for example, here it requires n moles of electron. N moles. That means n Faradays of current is required, or n coulombs of current is required. If you take the examples like this, Na plus ion, it undergo reduction to give sodium. Here 1 mole of electron. That means 1 Faraday of current is required. 1 Faraday, it deposits 23 grams of sodium. Similarly, Cu plus 2, it needs 2 electrons. So 2 Faradays of current that deposits 61.5 grams of copper. Similarly, if you consider aluminium ion, Al plus 3 electrons, that gives aluminium. So it requires 3 Faradays of current that deposits 27 grams of aluminium. Now, 3 Faraday deposit 27 grams. 1 Faraday that deposits 9 grams. Similarly, 1 Faraday that deposits half of this one. 30 point. Okay. So that shows. So you have 63 grams of copper. Okay. So 1 Faraday that deposits 31.5 gram. 31.5 gram is nothing but equivalent mass of copper. 9 gram, that is equivalent mass of aluminum. That means 1 Faraday of current that deposit 1 equivalent mass of the compound. So this is about Faraday's first law of electrolysis. Next, about Faraday's second law of electrolysis. So during electrolysis, when same amount of current is passed through different electrolytes, Mass of the compound deposited at any electrode is directly proportional to its equivalent mass. So according to second law of electrolysis, W is proportional to E. Now, consider two electrolytes A and B. A and B. Mass of A deposited is directly proportional to equivalent mass of A. Mass of B deposited is directly proportional to equivalent mass of B. So here mass of A deposited divided by mass of B deposited equals to equivalent mass of A divided by equivalent mass of B. Similarly, if you consider silver nitrate and copper sulfate, AgNO3 and copper sulfate, mass of silver deposited divided by mass of copper deposited is equal to equivalent mass of silver divided by equivalent mass of copper. So this is about Faraday's second law of electrolysis. Faraday's second law of electrolysis. Now, charge carried by 1 mole of electrons. Charge carried by 1 mole of electron. 1 mole of electron. Now, so charge of electron, that is equals to 1.602 into 10 to the power minus 19 coulombs. Okay. Into Avogadro number 6.022 10 to the power 23. So this is equals to 96,490 coulomb per mole, or we can take it as a 96,500 coulomb per mole, or is nothing but 1 Faraday. It is about charge carried by 1 mole of electron. Charge carried by 1 mole of electron. The next part is about electrolytic cells. So electrolytic cell comes under electrochemical cell. There are two types of electrochemical cell. One is called electrolytic cell and other one is called as galvanic cell. Electrochemical cell. And this first one about the electrolytic cell. Now, so what are called as electrolytic cell? So these are the cells which converts electrical energy to chemical energy. That kind of cell is called as electrolytic cell. And one more about the galvanic cell. So this is the device which converts chemical energy to electrical energy spontaneously. That device is called as galvanic cell. Simple example for galvanic cell is Daniell cell, combination of two half cells, two electrodes. Now, Daniell cell. So it is a combination of zinc electrode and the copper electrode. Or when two half cells, they are connected to a salt bridge, that results in the formation of Daniell cell. Now, so about the representation of Daniell cell, general representation. So, metal 1 and this is metal 2. These two are connected through a salt bridge. This acts as a left hand electrode. This acts as a right hand electrode. This is negative electrode. This is positive electrode. It's called as anode. In galvanic cell, anode is negative. Cathode is positive. Or with respect to reduction potential, Electrode with higher reduction potential is cathode. Electrode with lower reduction potential acts as a anode. Anode where oxidation takes place, cathode where reduction takes place. One example for galvanic cell, combination of zinc electrode and copper electrode. When zinc electrode is coupled with copper electrode, that forms a Daniell cell or galvanic cell. Now, the representation of Daniell cell by coupling zinc and copper electrode, where zinc is more electropositive. So, zinc is taken as a left-hand electrode. Zinc loses 2 electrons and it becomes Zn2 plus ion. Copper is less electropositive, Cu2 plus aqueous. These two electrodes are connected through a salt bridge. Now, anode where oxidation takes place, anode where oxidation takes place. Zinc undergoes oxidation. It becomes Zn2 plus ion. Okay. This is solid, aqueous. About the cathode, cathodic reaction. Cathode where reduction takes place. Cu2 plus, it undergo reduction to give Cu. About the overall reaction, zinc solid, Cu plus 2 aqueous, that gives Zn plus 2 aqueous and Cu solid. So zinc loses electron, it undergoes oxidation and it becomes Zn plus 2 ion. Cu2 plus gains electron and Cu2 plus undergo reduction to give copper. This is about the overall reaction taking place in galvanic cell where zinc and copper is coupled. Now, next about electrode potential. So what is called electrode potential? Is the potential developed when metal is in contact with its own ions. Thus developed potential is called as electrode potential. Now, and it is represented as E. Okay. Next one, standard electrode potential. Standard electrode potential. Standard electrode potential. It is E naught. It is the potential developed when metal is in contact with 1 molar solution of its own ions at 298 Kelvin and 1 bar pressure. Thus developed potential is called as standard electrode potential. Now, see, now to relate electrode potential and standard electrode potential, we can go for Nernst equation. Before that, let me explain about the term EMF, electromotive force, EMF. CMF is calculated using electrode potential of the cathode, electrode potential of the cathode and electrode potential of the anode. E, right hand electrode and left hand electrode, right hand electrode and left hand electrode, or E positive minus E negative. Okay. EMF of the galvanic cell is always positive. EMF of the galvanic cell is always positive. Now, so this is about electromotive force. Electromotive force. Now, next about the E naught of the cell. Standard electrode potential. Okay. It is sum of the oxidation potential and the reduction potential. Therefore, E naught of the cell, we can write like this: E naught of oxidation that takes place at the anode, anodic electrode. Next one is E naught, the reduction. This is observed at the cathode. Some of the oxidation potential and the reduction potential. Electrode potential anode and electrode potential of the cathode. Now, so when only oxidation takes place, only oxidation potential takes place. Only oxidation potential. Oxidation potential. Now in this case, we can calculate E naught of the cell. E naught of the cell is equals to E naught of anode, oxidation takes place, minus E naught of oxidation is given as a negative, takes place at the cathode. When only oxidation potential is known, then we can calculate E naught of the cell using this relationship. Now, next about Nernst equation. Nernst equation. Nernst equation. Now, so now according to Nernst equation, for a metal-metal ion reaction, metal-metal ion reaction, okay, electrode potential, say, metal ion undergo reduction that gives metal, okay, metal-metal ion reaction. Here electrode potential of the metal-metal ion reaction, that is equals to E is equals to E naught minus RT by NF ln, okay, concentration of the metal divided by concentration of metal ion, or we can write like this: E is equals to E naught minus 2.303 RT by NF log of concentration of the metal divided by concentration of metal ion. Now, by substituting the value of R, temperature, and Faraday's constant at 25 degrees Celsius, 298 Kelvin, we get E is equals to E naught minus 0.0591 by N log of concentration of the metal divided by concentration of metal ion. Now, when concentration of the solid or liquid or gas in pure state at 1 bar pressure, it is always taken as, or 1 atmospheric pressure, it is always taken as 1. Therefore, concentration of the metal solid, it is equals to 1. Therefore, same equation we can write in this form: E is equals to E naught minus 0.059 divided by N log of 1 by concentration of metal ion. Suppose here if you write plus, then concentration of metal ion comes to the numerator. So, this is expression, simple expression for Nernst expression for metal ion reaction, metal ion reaction. Now, so next one. Okay. For a cell reaction or for a galvanic cell, first we will go for cell reaction which involves combination of zinc electrode and the copper electrode. For cell reaction, overall cell reaction is zinc solid, Cu plus 2 aqueous, that gives Zn plus 2 aqueous, then CO solid. Now, using this reaction, we can represent the electrode potential E equals to E naught of the cell, okay, minus 0.0591 divided by N log of the concentration of metal ion present on the right hand side of the overall reaction. Now, which metal ion is present on the right hand side? That is zinc, Zn2 plus, divided by concentration of metal ion which is present on the left hand side. So E is equals to E naught of the cell minus 0.0591 by N log of concentration of zinc ion divided by concentration of Cu plus 2 ion. When the concentration is same, log 1 is 0, where E is equals to E naught of the cell. E is equals to E naught of the cell. Now, next we will go for general representation. Now, consider a reaction AA, that reacts with BB to give X, X and Y, Y. Now, so in this case, E is equals to E naught of the cell minus 0.0591 divided by N log of X into X raised to the power X, concentration of Y raised to the power Y divided by A and B, like this. So this is about the general representation. And always remember this form is written based on the overall reaction. Okay. If zinc and silver electrode coupled together, the overall reaction is Zn solid plus 2Ag plus, that gives Zn2 plus and 2Ag. So here when you consider at the denominator Ag plus raised to the power 2. So this form is written based on the overall reaction of the galvanic cell. Now, so equilibrium constant from Nernst equation. How to go for equilibrium constant? Using Nernst equation. Equilibrium constant from Nernst equation. Look here. When equilibrium is achieved, E cell is equal to 0. Electrode potential of the cell is equal to 0. Now, therefore, 0 is equals to E naught of the cell minus 0.0591 divided by N log of. Now, when you consider this form, okay, that is equals to log K. So E naught of the cell, it is equals to 0.0591 divided by N K, log K. Next, about relations between standard free energy change and EMF. In a galvanic cell, the reaction takes place spontaneously. So delta G naught is negative. So work done, that is equals to minus delta G naught or delta G. Now using this, we can go for relationship between standard free energy and EMF. Now, standard free energy change and EMF. So your delta G naught is equals to minus NF E naught at standard condition. What is N? N is number of electrons flow. F is Faraday's constant. E naught is EMF of the cell. And there is one more form of equation where delta G naught is related to equilibrium constant. So here delta G naught is equals to minus 2.303 RT log K. So from 1 and 2, NF E naught, it is equals to 2.303 RT log K, or log K is equals to NF E naught divided by 2.303 RT. So from this form also we can calculate equilibrium constant. It's about the relation between standard free energy change and equilibrium constant. As well as standard free energy change and EMF. Now. Next is about standard hydrogen electrode. So when pure hydrogen gas is passed through 1 molar solution of hydrochloric acid in presence of inert metal like platinum at 1 bar pressure, that forms standard hydrogen electrode. Standard hydrogen electrode is represented like this. Inert metal is platinum. And hydrogen gas in 1 bar pressure. Then H plus ion. Strength of H plus ion is 1 molar. This is about representation of standard hydrogen electrode. And this electrode is taken as a primary electrode because both oxidation and reduction takes place. And electrode potential of standard hydrogen electrode is 0. E naught of standard hydrogen electrode is equal to 0. So in order to calculate electrode potential of the experimental cell, it is coupled with standard hydrogen electrode. When experimental electrode is more electropositive, it acts as an anode, where standard hydrogen electrode acts as a cathode. Similarly, experimental electrode is less reactive. It has got more reduction potential. It acts as a cathode. In that case, standard hydrogen electrode, it acts as the anode. So, in order to calculate the electrode potential of this cell, standard hydrogen electrode is used. Now, for example, when standard hydrogen electrode is coupled with zinc electrode. Now, between zinc electrode and standard hydrogen electrode, zinc electrode is more reactive. It acts as a left-hand electrode. And standard hydrogen electrode, it acts as a right-hand electrode. And it's connected with potentiometer. Now, EMF, that is equals to E cathode, E right-hand electrode, minus E left-hand electrode, Whatever reading is given in this, that shows the EMF. Okay. So by knowing the EMF, which is right-hand electrode, standard hydrogen electrode, this is standard hydrogen electrode. No. This is left-hand electrode. This is always 0. Therefore, EMF becomes negative. That is electrode potential of the left-hand electrode. Now, similarly, when zinc is coupled with copper electrode, standard hydrogen electrode is coupled with copper electrode. It is coupled with copper electrode. Copper is less electropositive. It acts as a cathode. Now standard hydrogen electrode, it acts as the anode. Okay. It gives EMF, that is about 0.34 volt. I'll write directly 0.34 volt. It is equals to E cathode, that's copper, and E anode, standard hydrogen electrode. This is always 0. Therefore, electrode potential of the copper is plus 0.34. Therefore, standard hydrogen electrode, it is used to determine the electrode potential of the experimental cell. Now, next, quickly moving on to electrochemical series. It is a series of standard electrodes arranged from top to bottom in the order of decrease in reduction potential. Among these standard electrodes, again, hydrogen is taken as the standard one. Okay. Now, when you arrange the electrodes, fluorine, it comes at the top. It has got positive value. Lithium, lowest negative value, minus 3.05. So, standard electrodes are arranged from top to bottom in the decreasing order of their reduction potential. This series is called as electrochemical series. Now, what are the application of electrochemical series? According to this arrangement, the metal which are placed below hydrogen, they are having negative reduction potential. They are more reactive than the metal which are placed above hydrogen in the electrochemical series. And metals which are placed below the hydrogen, they can displace hydrogen from water or dilute acid. So, sodium is placed below hydrogen. Therefore, sodium on treating with water, that forms sodium hydroxide liberating hydrogen. Zinc is placed below hydrogen. Therefore, zinc is more reactive. On treating with sulfuric acid, it liberates hydrogen. But copper is placed above zinc. Copper is placed above standard hydrogen electrode. That is less reactive. Therefore, it fails to liberate hydrogen from dilute acid. So, this is about the applications of electrochemical series. Now, next part is about types of commercial cells or batteries. There are two types of cell. One is called as primary cell and other one is secondary cell. Primary cells are those cells which cannot be recharged. Example is dry cell, Leclanche cell. A simple example for primary cell. Dry cell. About the secondary cells. These are the cells which can be recharged. Such cells are called as secondary cells. So, example for secondary cells, lead storage battery. Nickel and cadmium battery, NICAD cell. That example for secondary cell. Next, about the fuel cells. Hydrogen, oxygen, fuel cell. So, what are called as fuel cell? What are fuel cells? Fuel cells are those which produces energy by the combustion of fuel. Such cells are called as fuel cells. So, in hydrogen oxygen fuel cell, hydrogen and oxygen is supplied to the cell in alkaline medium. Now, next part is about different cells, and here you should know which acts as the anode, cathode, and about the electrolyte. Now, we'll take some of the examples. So, name of the battery. anode, cathode, and electrolyte, Now, see, the first one, dry cell, Leclanche cell, dry cell. In dry cell, zinc container, it acts as the anode. And graphite rod present at the center, it acts as the cathode. Now, about the electrolyte, manganese dioxide, MnO2, with charcoal, it touches the graphite rod. Similarly, one more, ammonium chloride, NH4Cl, and zinc chloride, which touches the anode, zinc container. So this acts as the electrolyte. Now, so next one, second one is mercury cell. Both are example for primary cell. In mercury cell also, anode is zinc. Now, cathode is graphite. Now, about the electrolyte, mercuric oxide in alkaline medium, HgO, in presence of potassium hydroxide, it acts as a electrolyte. Now, next one, lead storage battery. Lead storage battery. In lead storage battery, lead plates, it acts as the anode. Lead plates coated with lead oxide, PbO2, it acts as the cathode. And 38% of sulfuric acid, it acts as the electrolyte. 38% of sulfuric acid, it acts as the electrolyte. Now, next one, after lead storage battery, fourth one, Nicad cell. Now, see, Nicad cell, which acts as the anode, cadmium, it acts as the anode. So when cadmium acts as the anode, the nickel dioxide, it acts as the cathode. So what about the electrolyte? Here also, it's an alkaline battery. So the reaction takes place in basic medium, potassium hydroxide. Okay. Now, last one about hydrogen oxygen fuel cell. Now, in hydrogen oxygen fuel cell, where the hydrogen gas is passed, that part of the cell, it acts as the anode, where hydrogen gas is passed. Oxygen gas is passed into cell, and that compartment, it acts as a cathode. Here also, the reaction takes place in the presence of concentrated solution of potassium hydroxide. So this is about different types of cell and which part acts as the anode and cathode with respect to their electrolyte. Now we'll see the production of current from these different cells, batteries. Now, so in dry cell, that provides, I'll write here, 1.5 volt dry cell. Now, say about the mercury cell, it produces 1.35 volt. Lead storage, that provides 2 volts. Now, Nicad cell, nickel and cadmium, Nicad cell, that is 1.39 volt. So among these one, the best one is hydrogen oxygen fuel cell because there is no environmental pollution. The rest of the cells that leads to environmental pollution. So this is about the different types of battery. And here you should know the different types of reactions, the chemical changes taking place at the different electrodes, anode and cathode. Especially for lead storage battery, discharging process and recharging process. In discharging process, lead Pb, it undergo oxidation at the anode, that gives PbSO4. PbSO4. At the cathode, PbO2, it undergo reduction. That also leads to give PbSO4. PbSO4. That's during discharging process. During recharging of lead storage battery, reverse reaction takes place. Lead sulfate that dissociates to give Pb and PbO2. In the first dry cell, at the anode, zinc undergoes oxidation to give Zn2 plus ion. Now, at the cathode, MnO2. Okay. MnO2 in presence of ammonium ion, MnO2 in presence of ammonium ion. That gives MnO with OH and NH3 ammonia. That ammonia combines with zinc ion to give a complex ion, Zn NH3 4 times plus 2. Okay. So this is about batteries. Now, so last part is about corrosion. Now, so what is called corrosion? Deterioration of metal due to the attack of constituents of environment. That process is called as corrosion. Now, simple example for corrosion: rusting of iron, tailing of mercury, a green coating on the surface of copper. So these are examples for corrosion. First about rusting of iron. When iron is exposed to moisture for a long time, tiny galvanic cells are produced. So anodic reaction where iron acts as the anode and dissolved carbon dioxide in moisture, it acts as the electrolyte and carbon acts as the cathode. So anodic and cathodic reaction takes place. First it gives ferrous hydroxide. Ferrous hydroxide converted into ferric hydroxide, and ferric hydroxide that gives hydrated ferric oxide. Nothing but rust. Color is brown. Similarly about the tailing of mercury. So mercury has got special property. It is a meniscus and shining. When it comes in contact with ozone, the mercury gets oxidized to mercuric oxide. And after the formation of mercuric oxide, it dissolves remaining amount of mercury in it. Therefore, mercury loses its shining and meniscus property. This is an example for corrosion. So after that, the mercury, wherever it goes, that produces tail-like capability. Therefore, it's called as tailing of mercury. It sticks to the surface. Otherwise, mercury will not stick to the surface due to meniscus property. Or a green coating on the surface of copper article when it is exposed to moisture for a long time. A green coating of basic copper carbonate is formed. All these are different types, example for different types of corrosion. Now, so about the prevention of corrosion. There are various methods. The first one is barrier protection. A barrier is placed between the metal and the constituents of environment, either by applying painting, or by applying oiling, or another metal by a process called electroplating. Now, next method is about sacrificial protection, where iron is coated with more electropositive metal. As long as this coating is present on the surface of iron, More electropositive metal undergoes oxidation by preventing ion. Similar to this, there is one more method that's called as cathodic protection. It is suitable for underground pipelines and also to prevent the body of a ship from corrosion. Where iron is connected to more electropositive metal like magnesium. So more electropositive metal, it acts as the anode. Now iron is less electropositive, it acts as a cathode. We are converting iron into cathode by connecting to more electropositive metal. Oxidation takes place at the anode. So more electropositive metal, it undergoes oxidation by preventing iron. This kind of method is called as cathodic protection. It's called as cathodic protection. Good. So this is about electrochemistry.